So where does the number e come from? So let's find out. The number e was developed by a mathematician named Leonard Euler, and when you see pictures of him, he's kind of blind in one eye, so he's always kind of off to one side. He was from the 1700s, a brilliant, brilliant mathematician. So why do we even use the number e? What's the number e used for? It's used in a lot of things, actually, but let me give you one of the most basic. Let's actually start with a banking problem, like we've been doing. I'm going to write this one out. So here goes. You deposit. The numbers are going to seem a little ridiculous, but it's going to help us develop an understanding of what E is. You deposit the most practical amount ever, $1, into an account that has, now it's going to get really unrealistic right here, but it's going to help us develop the number E. It has 100% interest. Yeah, right. Oh no, my marker's dying. Compounded. Let's just start with annually. That's once a year. Annually. Oh no, my marker's dying. It's okay, I have another one. I have another black marker somewhere. Here it is. Compounded annually. How much is in your account in 1 year? Is in your account. It's dying too. In 1 year. Okay, I picked some numbers that will help us figure this thing out. So let's start by switching markers because this one's dying. And then let's go here. Let's go to the correct formula, and A equals P 1 plus R over N to the NT. And we're going to develop what E is. Well, first of all, P is $1. 1 plus R, and we're going to move the decimal 2 places, and it makes it 1 over N, and annually is once per year, and we're going to raise it to the N times T, so 1 times 1 year, and 1 times 1 is just 1. Let's simplify a whole lot of this. Basically, we have, let's just be realistic, we have 1 times 2 to the first power, we have a 2. Okay. I'm going somewhere with this. So over here, let's just say that if N is 1, then the amount that we have is 2. Alright, let's change the wording of this problem just a little bit. Let's make it, I erased it. Let's not. Let's just call it semi-annually. And if I say it's semi-annually, then it happens twice a year. And since it happens twice a year, we'll change this to a 2. And we will change this to a 2. Since it's multiplied by 1, we're just going to start leaving that off. That exponent's multiplied by 1. Alright, so we have 1 plus 1/2 to the second power. That is 1.5 squared. 1.5 squared is 2.25. So when N is 2, we get 2.25. Okay? Let's keep going. What we're going to do is keep changing this word, and as we change this word, we're going to get to a value that it's going to kind of zero in on, for lack of a better word. It's going to approach a certain value, and that value that it's going to approach is going to be E. Years ago when I would teach this stuff, students would say, Mr. Reader, why wouldn't you want your interest to be compounded continuously? Because you're just going to get like an infinite amount of money. And I said, no, the formula is built, and E is built in such a way that it's not going to be like you're getting a ridiculous amount of money. Because at some point it's just going to level off. And you're going to get just a little bit more, but it's not enough to even count. So let's go to the next obvious one. That would be quarterly. And if we go quarterly, then I reach a point where I can't do this in my head. So, yeah. 1 plus 1/4, we're going to raise it to the 4th power, so 1.25 to the 4th power, 1.25 to the 4th power, and we get 2.44. 2.44. I'm going to start writing more than 2 decimal places, even though we're dealing with money. I'm going to write several decimal places, 140625. Okay, so let's come over here, and we'll write that down. So when it was 4, we had 2.44, 140625. Mr. Reader, where in the world are you going with this? Well, thanks for asking. I'm about to tell you. I'm going to calculus. For real. One of the elementary concepts in calculus is that the idea of a limit. It's the idea that we're going to approach a certain value and see what it becomes, what it rounds off to be. And often it rounds off to be a nice whole number. For example, if I say, the value is x approaches whatever of whatever, and it ends up, as you get closer and closer to that value, it's like 0.98, 0.99, 0.999, 0.9999. You look at that, and after a while you just say, you know what, that rounds to 1. So it's approaching 1. What we're going to do is find out what the value of e is by plugging in larger and larger numbers. So if you really want to get technical about it, we're going to let n, this value right here, approach infinity. Now obviously we can't plug an infinity in for n, but, let's go monthly here, but we can plug in larger and larger values until we say, you know what, that's close enough of an estimate, so we'll just go with that. Alright, get my eraser and let's erase some stuff here. Now again, p is 1, t is 1, r is 1, and that's going to help our calculation quite a bit. So I'm going to leave off p, 1 plus 1 over 12 to the 12 times 1, and then we plug that into our calculator. 1 plus 1 over 12, and we'll raise that to the 12th power, and we get 2.613035529. Now, I hope you realize that up to this point, it's like 2 and then some change, and it's slowly growing. So, if we compound interest 12 times a year, we get 2.613035529. Alright, let's go crazy with it. Let's compound our interest daily, which is the way most banks do it. That changes this 12, that changes this 12, that obviously will change this answer. So let's change this to a daily, right there. Changing this to a daily means that is 360, that is 360, and I clearly cannot do this in my head. 1 plus 1 over 360, raise it to the 360th power, and we get 2.714516025. Okay, we're getting really close to the actual value of e now. So if I make this 360, then it's 2.714516025. Okay, I'm going to go real crazy on this, and I'm going to say that you open an account, and it's going to compound your interest 10,000 times a year. 10,000 times a year. So it's not quite continuous, but it sure is a whole lot more than daily. So if I say compounded where n equals 10,000, now what we're doing is plugging in an enormous value, and we should be able to see what it's really approaching. So let's do that. P is still 1, so 1 plus 1 over 10,000. There's going to come a point where the calculator is not going to be able to do this, and hopefully this is not it. 1 plus 1 over 10,000, and we raise it to the 10,000. This gets interesting. 2.7, oops, 2.718145,927. We'll come over here and I'll put it in our little table. So if n was 10,000, then we get 2.718145927. Okay, let's just go ahead and go for the big one. Here's what we're about to do. We're going to plug in 1 million, where n is 1 million. And then we're going to see what happens. And we should get a value that is very close to the actual value of e. This is really close. 2.718 is like up to the nearest 3 decimal places accurate. So it's 1 plus 1 over 1 million to the 1 million. Alright, here we go. 1 plus 1 over a million to the 1 million. Alright, we're good. 5 decimal places. We get 2.7, did it again, 2.718280469. And let's just come over here. We're going to quit calling it 1 million. We're going to call it 10 to the 6th power because that's what it really is. And we get 2.71828 and then some change. 0469. 0469. So the bigger this gets, the more accurate it gets to our actual answer. So let me write this out in calculus notation because you might see this again whether you take calculus or not. And it's a very practical notation anyway. Here it is. This is the limit. LIM stands for limit. As n approaches infinity, so we're going to plug in bigger and bigger values of this little guy right here. 1 plus 1 over n to the n power. Notice again in the original problem we let p be 1, r be 1, and t be 1, and that just helped us figure it out. And as we do that, we get the actual value of e. I say the actual value of e. I'm going to round it off. It's 2.71828. 1828. Obviously, this one was not quite accurate enough. It looks like it repeats, but it does not. It does not keep repeating 1828. 2.71828, 1828, and that is E. I'm going to put approximately because obviously we've left off some decimals, so it's E. If you want to be technical about it, I could put ... and then make it equal E. So that is where E comes from. So what's it useful for? It's useful for banking formulas. This is the, rounded off, exact answer for E. When your interest is compounded continuously, it doesn't just grow at an incredible, unrealistic rate. It kind of levels off to a certain point.